And what is the information that you have? The information that you have is historical information, which comes from the weather prediction and the observed loads. So you have a weather prediction today, and then you can look what the demand was yesterday. Is there any data available? No, there's infinite amount of data available. So it seems that this is a job for a statistician, right? You immediately go to a statistician, you say, I have millions of pieces of data. This is just in New England, and you probably won't be able to see this, but this has it divided in particular zones: Western Massachusetts, Eastern Massachusetts, Connecticut, and so on and so on. For each of these regions, you have a particular day. And so you have thousands and thousands of days and lots of information. But then you start to analyze the information. And when you start to look at the information, you are eventually going to be in the opposite. You're going to have a lack of data. And I'm going to explain why this occurs. If we look at a week, and we look over a month, or 8 weeks in this case, we see that there are days when the demand is at a certain level, higher level, and points where there's a lower level. Well, these are weekends. Okay? At that time, the load demand is much smaller. At the high points, I don't know why there are specific high points. Apparently, people use a lot of electricity certain days. And we see there's a weekly pattern which emerges. Actually, you see it even per month, something similar taking on. If you follow just the blue line, you see it actually waving in a certain way. Now, in order to get enough data, we are going to introduce the following operation. We're going to make a transformation which takes the prediction and loads so that the predictions we don't have to do anything about, but the loads, so that they are all Wednesday loads. That's very easy. It's a simple transformation of every day so that it corresponds to a Wednesday. But you have other issues that come up. Namely, if you look at the summer in July, you see that there's if you look at the relationship between the load and the temperature, there's a definite tendency which takes place here. And similarly, if you look at not just temperature, but also humidity, so that the loads that you can predict have a relationship between temperature, humidity, and they follow a certain pattern. So load versus temperature is given here. Load versus humidity is, you obtain this on 52 days. This suggests the following: that what you should not try to estimate load, to find an estimate of the load for a particular day, simply based on having some data. You really should divide the year up in segments. The winter will be a season. The summer you will handle differently. So you will do that. And in the summer, you will, and this is in particular useful in New England, where there are days where it's very high temperature and high humidity. There are normal summer days, and then there are cool summer days. So not only you divide it in seasons, but you divide it in sub-seasons. In the winter, humidity plays relatively no importance, but cloud cover does. And you will have, again, a subdivision of each of the winter seasons into sub-seasons. So instead of having 365 pieces of information for a year, you end up for each season having about 20 or 25 days in the sub-season. So since, at least in the United States, there was an economic change which happened after 2009, where actually the consumption of electricity dropped tremendously for a while and continued in that way since then, since the economic conditions have changed, actually all what you have is 25 days each year for 5 years. Okay? 2009, 2010, 2011, 12, up to 2013. So now you have 125 points. Now if you go to a statistician and you say, I'm trying to estimate something which is in dimension 24, because that's what you are predicting, is the load for each hour during a day, and I have 125 points, they will say, we cannot do anything. If dimension, in order to